There were some questions that people struggled with in class today, and we took a little while to take up one of them, but I wanted to show you some of the other, first of all, the other question and the other approaches to the question we did take up. So let's look at question 4 from today's work, which was that you draw 3 cards from a regular deck of cards, the 52 card French deck, and the question is, what is the probability that you have a pair? So if we call that event A is the event that you have a pair, then the question is to find the probability of A. Now, we talked about how it's a little bit ambiguous. Do you mean that you have exactly a pair, or that you have at least a pair, maybe more than one pair? So for example, we have to consider, what if you have like the 9 of hearts and the 9 of diamonds and the 10 of hearts? That obviously fits because you have that pair of 9s. But what if you have the 9 of hearts, the 9 of diamonds, and the 9 of spades? And so the question isn't clear, and that's okay. We need to clarify these things when we're solving problems. This you might call a 3 of a kind, and so you might not count it in your calculations, and that's fine. Either one is fine. That's the sort of thing that I'm comfortable with seeing either solution for, and it's kind of the same amount of work either way. So in order to solve this, we kind of want to we need to count how many outcomes are possible. So first, I suppose we can count how many total ways there are to have 3 cards, to get a hand, if you like, of 3 cards from a French deck. So we're going to need that information in any case. So let's do that. The total number, if you like, of 3 card hands isn't that hard, actually. There are 52 cards in the deck, and we're going to choose 3 of them. So that's 52 factorial over 49 factorial 3 factorial, which, if you want to expand it out, is 52 times 51 times 50, all divided by 6. The 49 cancels off a whole bunch of the stuff from the 52 factorial, and you're left with 3 factorial on the bottom, which is that value 6 there, which I have down as 22,100. So this value here is the size of our sample space, or our universal set. So we're going to use that when we do that calculation of probability in just a moment. So let's look at these 2 cases separately. What if we count only the cases where we have exactly a pair but not 3 of a kind? So this is what we did in class. I'll call this case 1, or sort of version 1. So to do this, we're going to select 3 cards, and 2 of them have to be a pair. So looking at this same example of 9 of hearts and 9 of diamonds, we're going to choose any card in the deck. There are 52 cards, and we're going to choose one of them. So we could have just written 52 here, but 52, but I like to use the combination notation here. We're going to do it a bunch. And then once we've selected that card, there are only 3 other cards in the deck that match it. So there are 3 cards, and we're going to choose one of those. Now, the order that we choose these in, though, doesn't matter. If I choose the 9 of hearts and then the 9 of diamonds, that's the same as if I had chosen the 9 of diamonds and then the 9 of hearts. So we need to divide by the number of ways to arrange those 2 items. That's 2 factorial. And then once that's finished, once we've selected those 2 cards, if we're doing this version here where we have exactly a pair, then we only have now 48 remaining cards, because we're not allowed to use, say, the 9s anymore. And we're going to choose one of those. So let's make some calculations here. This is 52 times 3 times 48 all over 2. And I have that working out to 3,744. Now, another way to approach this is to say, well, let's first choose the value, like 9, of the pair of cards. So there are 13 values, and we're going to choose one of those, let's say the 9s. And then once we've done that, we're going to select 2 of those cards. There are 4 9s, and we're going to pick 2 of them, say the heart and the diamond. And now, because this is a combination, the order already doesn't matter in here. This is 4 factorial over 2 factorial, 2 factorial. And then once again, we're going to choose our non-matching card. So when you work this out, this is 13 times, and I'll write out the whole thing, 4 factorial over 2 factorial, 2 factorial, times 48, which is 13 times, well, 4 factorial over 2 factorial, 2 factorial is the same as 4 times 3 times 2 times 1. Divide out the 2 times 1 and another 2. So this is actually just going to be the same as 4 times 3 over 2 times 48. Let me just make this a little longer. You see here, look at this. 13 times 4. That's the same as the 52 up here. So you can see that these values are actually going to be the same. 3744. So that's counting the cases where the 3 of a kind does not count, these ones here. So let's consider the alternative case then. What if we do count those? So I'm going to call that case 2, the cases where 3 of a kinds do count. And a couple of ways to do this. One way is to just add on to what we've already accomplished. So we could say, well, that's taking all of the pairs that are not 3s of a kind, and we're going to add on the number of ways to get exactly a 3 of a kind. Well, to do that, you take 13 values and select one of them, and then you have 4 suits, and you're going to select 3 suits to be your part of your 3 of a kind. So this would be like saying, okay, we're going to select a value like 9. There are 13 ways to select a value. And then from the 4 suits, we're going to choose 3 of them. And if we, so this will end up being 3744 plus, this is times 13, and this is times 4. So 13 times 4 is 52. And we're going to end up with 3796. All right, pretty good so far, but there is another way to approach this. Let's get a fresh sheet here. Instead of calculating it directly, we can calculate this indirectly. So let's say we take all of those cards, all of those hands, 52, choose 3 hands, and let's subtract away the ones that don't have any duplicates. We want to make sure we have at least a pair, so let's just find the ways to choose 3 cards that are definitely not going to give us pairs. So let's choose a first card, 52, choose 1. Then we have to choose a second card that doesn't match. There are only 48 cards that don't match, so we'll choose one of those. And then so we've used up 2 values so far. Let's choose another card. There are only 44 left that don't match. We'll choose one of those. But each of these 3 cards could have come in any order. You could have chosen an ace and then a 9 and an 8, or you could have chosen 8, ace, 9, or any order. So we have to divide by the number of ways to arrange those 3 cards so that we end up with what's more like a combination instead of a permutation. So we can do this. We already have this value from before, 22,100. And this mess right here, we're going to work out 52 times 48 times 44 all over 6. That's 22,100 minus, well, actually minus most of them. This is 18,304, which comes out to 3796. Okay, well, we're pretty close to finish now. So in these 2 ways, we've got the probability of A is going to be, now we have either this value here, 3744, over 22,100, or we have the other value, depending on which case we're doing, 3796 divided by 22,100. And I haven't actually worked that out to a nice fraction. I can see that it will reduce, but reduce either one of those to get to a solution that you're looking for. Okay, the last one, we had one more question, 5. that was about rolling a die. And you roll a die 3 times. And the question is, are you more likely to A, have an increasing sequence? And I explain in the question what kind of sequence I'm looking for. Or are you more likely to B, roll no prime numbers? So let's look at what each of these is. The nice thing about event A is we can actually list all of the outcomes. A is simply this set. We can get 1, 2, 3, or 2, 3, 4, 4, sorry, I'm missing one here, 3, 4, 5, or 4, 5, 6. And I explicitly said that you can't have things like 2, 4, 5. You can't skip any numbers. So there are only 3, 4 different outcomes. So the size of set A is 4. So let's look at B, not having any primes. Well, the primes are 2, 3, and 5. So the non-primes are 1, 4, and 6. So if I'm going to roll a die 3 times in a row, there are 3 ways to get the first value, 3 ways to get the second value, and 3 ways to get the third that are none of them primes. So the size of set B then is 3 times 3 times 3, which is 80, let's see, 3 times 3 is 9, times 3 is 27. So there are 4 sequences of rolls that will give us an increasing sequence like this. There are 27 sequences of rolls that will not give us any prime numbers. So I don't need to get to the probability stage. I can say that since each outcome is equally likely, the probability of A is less than the probability of B. That is, that B is more likely. If I wanted to, I could also count the total number of sequences there are. So I could say, for example, the size of the sample space of the universal set is 6 cubed, 6 values for each of the 3 rolls, which off the top of my head is 216. So then you could then calculate the probability of A is 4 over 216, and the probability of B is 27 over 216, and you can compare with those fractions instead of just with the sizes of the sets. Okay, so those are those 2 questions in a bunch of different ways, and as always, please ask questions.